All right, well, welcome everybody. So the DPRG monthly meeting for August of 2017. And today, my name's Carl Ott, and I'm going to walk you through the current state of my line follower project and a few other things. So let me switch to the screen. And here we go. So I should be sharing the screen now. Is this true, Steve?
Yes, that's true.
Okay. So, let's start off. So, you may or may not be familiar, but the Robot Club has a line following course, and well, if I were to put this course up, what do you think this is in the audience? What do you guys think this is?
Met.
All right. So, if you thought it was the line following course, that's not the answer I was looking for. This is more like the straight line trajectory that my project has been following. So not exactly straight line. It's also kind of the course that we're going to follow through today's little talk. So I'm going to bounce around all over the place. For those that might not be familiar, this is where you can find the latest rules and PDF copy of this course. So today I'm going to give a kind of a virtual demo just of where it is. It's not done, heads up, so there's no need to gripe about, yeah, it gets stuck here or there. I know that. But unlike any time in the past, I'm more prepared now to have a kind of quantified date as to when it's going to finish and I'm going to get done. So I'll show you where we stand, show you a high-level architecture of the project, since I guess it's a little different from many of the robots in the club. And then also, since I think probably not many people mess around with JavaScript or Node in the club, I'm going to share some things that I found interesting coming from a background of, well, my last formal course in computer programming was Pascal and Carnegie Mellon in the 80s. So
it was in the last millennium, wasn't it?
It was.
Yeah.
It was when object-oriented programming was a dream in somebody's eye in the labs, and they were just starting to think about maybe we should do this thing called C++. So my courses predated that kind of. They were right in the world where they were thinking about the object-oriented mentality. So I've had a ways to go figure stuff out. So let's flip over to this demo. So basically, yes, this is the line following course, and what I have is a kind of a simulation of the course and a simulation of a robot. So this is the code that will ultimately drive a real robot. And so there's actually three pieces on the screen. This is RoboRealm. This in the middle is the Node service, Node server, and then this is the UI, which is a web browser. So what I can do is I can say, okay, let's start, and then I can cut it loose. And now with all this stuff going on this laptop, it's down pretty slow now, a couple hertz. When I'm not trying to do screen scrapes for Join Me, it'll go up around 10 hertz. And the Vision core itself is around 20 hertz right now. So you can see that if I virtually pick up the robot and drop it down, like let's drop it down around waypoint 4, and then I say cut it loose. Now it's at waypoint 4, and you can see this is right around here. It's heading into this blotch where there's really low contrast. And then if I turn it loose, you can see that it's analyzing the image, and it's looking at the lines it sees, and it's picking a place to go, and then it gets stuck because I haven't written that part yet. So you might remember past versions of this where it would go at like 1 hertz or thereabouts, and there were other issues it was having. It would get stuck a lot on just the communication side. And that's what a lot of this talk is about today, is the things I had to do to get past it. But you can see it kind of finds its way around and keeps going, and despite all that clutter in the image, until it hits a nice 90-degree angle, it gets stuck. It goes well, pretty well. And even here, if we jump down to waypoint 8, so heading into the home stretch. There we go. Do it again. Yep, there we go, start. And it just finds its way.
So it looks like it's picking up the tile edges a little bit.
Sometimes, yeah.
Okay, but okay, you've got that sort of tuned out where you're not
Yeah.
seeing those.
So there's several levels. We'll get into it in the architecture, but there's several levels of what's going on here. And in simple words, the first level is kind of the image processing. So it just takes the picture and looks at the pixels and does things to the pixels, and it returns an array of lines, candidate lines. But then the next level is, because there can be more than one line, there usually is, that the next logic has to figure out, well, which line is the right line and where do I aim?
And you're color coding those, is that what we're seeing?
What we're seeing is that the base image looks, literally I took the PDF off of the DPRG website. So it starts as grayscale, and then I've added these colored so I can know where the waypoints are about. And then what you're seeing is superimposed on top of the simulated view of the robot, you're seeing this white line is part of the image processing that's fed to the node code. And then the node code says, well, based on that, I want to aim for this particular line, so then it tells RoboRealm to draw a yellow arrow.
Well, answers that we see in addition, why is that? Sorry, is that
Uh,
local there?
That'll show up in the presentation, but yeah, exactly. But just at a high level, so this is you can see that it's moving along, and yes, the world's not perfect. So if the robot is coming into that particular stretched little off angle, and we turn it loose, well, it'll more or less self-correct. And the X's are, for any given image frame, what does it think the candidate lines are from the vision processing? You see here, it kind of goes to the intersection. So what I have to do next is, and one of the nexts is when we get to this waypoint 9. Okay, let's go there. When I get to this waypoint 9, I have to train it that, or write the algorithm that says, yeah, don't take angles to the left if there's a straight through. And if there's an angle to the right and a straight through, then instead of going straight through, then we'll take this right one up here. But I haven't written that part yet. That's yet to come. So that's a snapshot of where it is. And that's the simulator. So ultimately, it'll replace the simulator with the real robot and communication between a platform. But that's in the next part of this here. So, and we can bounce back and forth if we need. So, all right. So now, let me jump into here, and then we can always bounce back and look at it if we need. So what I have in there is 3 different parts, right? So I showed you there's this web page, that's the control, it's the user interface. And I've tried to, I didn't want to worry about UI too much, so I made it so that I could write it once and then not muck with it until a lot later. So it's kind of crunchy, but it just controls, right? And it lets me tell the simulator what to do and tell me what the robot what to do. And then over in RoboRealm, the RoboRealm has really 3 parts. And it's got the simulator, so it's got this kind of virtual course logic. It's got kind of a really simple-minded representation of the robot, so it's got a virtual robot. And I think of that as the simulator parts of it. And then it has this vision, this image processing bit. And then it has, when we're looking at this screen, we're literally looking at the RoboRealm IDE, RoboRealm runtime thing. So rather than try and take that image and go port it and import it back into my UI, I said, let's keep it simple. We'll just use this as a visual feedback for what the simulator is doing. So it saved a lot of coding in a way because this was already existing in RoboRealm. And then, go ahead.
Carl, is the image, if you back up there, is that image representative of what camera angle down at a certain angle on the robot would see?
Well, no. Well,
No.
yes, it depends, right? So if
No, yes, it could.
if the robot has one of these arms that goes out front with the camera facing down, then yeah, it would be representative. But probably for most of our robots, it's going to have a downlook angle. So in that respect, no, it's not representative
I see, because there's no spread in the image
with the straight down.
Yeah.
But if there was a spread in the image, there's actually a couple of things to consider. First of all, RoboRealm has perspective correction.
So you just tell it the angle and it'll straighten it back out?
Yeah, so I could do that within RoboRealm. But then the next thought is that, well, depending on how orthogonal the different algorithms are that I have to detect these different coarse constructs, it could very well be that they're tolerant of angle, that they don't really care. So I'm keeping that part of it simple for now, and just assuming that it's a straight down. And once I get this virtual robot to go around the virtual course, and then once I replace this simplified version of the course with the real one that has these contrast changes, nasty little contrast changes, once I conquer the course in the simulator, then I'll start worrying about those real world effects and folding those in.
And is the assumption that the downward, the downward looking angle that we're looking at right now is in the center of the robot or out front, in front of the robot?
Does it matter? It's just a bias. I think it's probably in the center right now. But I have no, actually, okay, I lied. The way the assumption is that I've coded it so that the nose of the robot is literally right here. This is 160 by 120. So this is 80 and 0 is where I figure the nose is the robot.
So our camera would be on an arm or something out in front, looking
Yeah.
down right in front of the robot.
Yeah. But that's one of those, I mentioned this is a virtual, very simple approximation of the robot, right? So I haven't really worried about those kinds of bias offsets. But obviously when
Get one thing working first.
depending on how clean I want it to be, right, and where, because you can put those offsets in to the algorithm, you can imagine, right, so that it knows that if that's the point where it should be turning, and it's going to take X amount of distance before it turns, then we'll add that offset in. To be determined.
There you go, to be determined.
And that's been an interesting thing about this project, right? Because there's so many different ways you could push on it and improve it and prettify it, and there's so many different things you could do with it that you just got to pick your pain and get started. Like one thing that I think would be fun, the club is interested to fund little side projects, and one of the things I thought earlier this year to put on the table would be cool to do, would go to get a brushless gimbal, a 2 or 3 axis brushless gimbal. Put a laser pointer on it, and I could put that laser pointer on the physical robot, and then the physical robot, once it figures out where it wants to go, it could put the laser pointer on that point on the course. That would be pretty cool, wouldn't it? Yeah. But there's only so many days in a year.
Back to work.
Back to work. So before all that, I got to make it all the way around the course, right? And you got to make it around the virtual course. You got to get it around the real course. So this is with the approach that I took, it's taken a little longer than I had forecast. Just a little. So. Yeah, so the UI is in a web browser, and the simulator's over in RoboRealm, and the robot vision is in RoboRealm, and our kind of feedback is in RoboRealm. And then in Node.js is the server that's where the main robot logic is, and some middleware that goes between the UI and RoboRealm. And quite frankly, if we look at, I have a timeline on another slide. If we think about the 2.5 years that I've been playing with this, probably 80 or 85% of it has been with this Node.js stuff, just because it was just because RoboRealm actually made the vision part really easy. I knocked the vision part out really quickly. And then I hit Node and realized just how out of date my software background was. So at a high level, does that make sense?
Yeah.
Okay. So now let's look at the UI. UI is pretty simple, like I mentioned. You got above this line here is just a simulator. That part becomes irrelevant when there's a real robot in the room. And then this part below is the real robot. The real robot, I have these three programmable buttons, each for robot, each for simulator, so that I can assign like test code in the node without having to redo the UI. So when I need to exercise something, I can just push one of these buttons and try something out. And then, so their functionality changes. But at the end of the day, the robot currently has really just 4 buttons. It has one button to step, so I can move forward 1 step. This is an event loop driven kind of a robot, discrete thing. I can start it and then just turn it loose on its own, or I can stop whatever it's doing and I can re-initialize it. So that's consciously and all this other space is for, I thought ultimately, well, yeah, it'd be cool to have onboard diagnostics, to have a state machine indicator, to have a dashboard. Many directions that this could push, right? And even for the simulator, if I was more interested in HTML and more UI design, why wouldn't I take the feedback of the position on the course and put a little HTML representation of the robot on the course right here in the simulator page? And I wouldn't, because I wanted to work on the robot first, and it's only so many days in a year, right? So that's the UI. And then this is the node part. A lot going on here. So it's got these APIs around the edge, right? It's got one I like to think of as for the simulator. It's got an API for the robot control. It's got an API for RoboRealm. And since RoboRealm has both the simulator and parts of the real robot, there's kind of interesting stuff going on here. That's been part of the challenge, is that in a way the simulator and the robot are asynchronous. So I've had a lot of what I'm going to show you on here has to do with how do you synchronize different events that are basically asynchronous. But it's especially difficult or challenging for me because all of those commands were going over the same interface, the same API to the same target. So I had to put a lot of coordination into this code. Then down below, so the robot controller, it has it figures out the order of things to do, and it queues them up and runs them in order. It figures out how to interpret the feedback from the image processing, and then it figures out, okay, based on the feedback, how do I move? Where do I go? What commands do I use? And then I have to issue them. So these parts are grayed out because they're placeholders for the real robot later on. For now, everything's in RoboRealm, so like the simulator sends both vision, image information back and forth, as well as movement commands. Whereas the robot controller directly gets feedback for the vision from RoboRealm, and then through this budding abstraction layer, the robot controller has to decide, is it going to send commands to the virtual robot or the real robot? Right now there's no real robot, so there's not much of an abstraction layer, but ultimately I'd expect to have a kind of a switch in here where you could run it in real mode or simulator mode. So that's what's going on in the Node.js thing. Now the simulator, again, this is mostly RoboRealm, and it's pretty simple. It really is. I don't think this took more than a weekend or two to knock out, if that. But most of it was one afternoon on a Saturday. And it simply takes, it reads in that entire course, that entire PDF, it reads it into RoboRealm, and then you give it it assumes that the camera is going to return a 160 by 120 image. And it says, okay, you tell me what position and orientation, so x, y, theta, and then I'll return an image from the course that corresponds to that position on the course. Really simple. And then so it's got a static image of the course. It's got some really simple JavaScript helper things that interpret the x, y, theta and convert them to RoboRealm space. And then it also accepts move commands. Now, right now, since this is a iterative, discrete, event-driven kind of a thing, it takes deltas. So I wanted it to be platform agnostic. So I can take a differential drive robot that just has front, back, or spin heading, or I can take one with omni wheels where you can have left, right, as well as front to back and spin. So the simulator accepts all three of those. And right now the simulator accepts deltas. So its units are pixels with respect to the course image. So it's all hard coded to how many pixels is this image. And this happens to be 160 by 120 for reference sake. So that's the simulator part, and that logic is mostly in RoboRealm. Then the next part in RoboRealm is the vision process. And this took a little bit longer than the simulator. This was a bunch of hours, a few days over a number of months to figure out the algorithm that you see now. But because of the way that RoboRealm lets you quickly just grab these pre-compiled modules and stack them up in a script and pipeline them one after another, it was actually, I say, really very quick to get from this to here, and to have a single script that behaves really well over the entire course. So, at least with the single contrast course. I'm going to have to change the script to get the real course where it flips from black on white to white on black.
How are you going to detect that?
What I'll do is edge detection. So, and the reason I didn't start off this way is that I didn't have enough node logic in place ahead of time. So if I have, let's imagine that, let's go up to this course. Let's say you do an edge detection across this thing. So even if you can subtract out most of these gray areas, you're still going to have a lot of crossroads intersections, right? And for each line, you'll have 2 lines. You'll have the line on each edge. And that algorithm is actually really simple to write. It's fast to execute. But then you have all these intersections that you have to get through. And at the time I got started on this, I didn't have that intersection logic figured out. Okay, so let's take a little detour. So how is the image processing going to work? Actually, if we can come back to that.
Sure.
Let's come back to that. So we have a simulator that takes a whole course and returns a virtual view of what the virtual robot would see.
What? I'm sorry. Just to be clear here, the image that we're looking at there would be the one that was fetched by the simulator given a position of 0, 0, and a theta of 0. That is the start, finish line?
These coordinates are absolute coordinates with respect to
image.
whatever this image is. But the simulator kind of normalizes it because the node, this code up here, it doesn't know about. I had to assume it doesn't know about the whole course. So the fundamental assumption is it knows the different constructs of the rules of the course. So in other words, and I can see this is bothering you, so we're going to go there now. So if you look at the rules of the course, it defines, and I could pull those up too, actually, I didn't, but let's pull those up. This is a useful detour. The rules are here. Right, to control, follow. Yes, it's okay. It's safe. What screen is it? All right. So the way the challenge is designed is that the novice course just has these primitives: straight lines, turns, and they all go in right in the middle of the edge of the tile. Okay? And they have special specificity, but I don't care about that for now. The advanced course gets to be a little more interesting. So maybe the tiles are offset, maybe you have these discontinuous lines, maybe you have this big gap you have to go across, maybe you have these 45-degree angles crop in, or 9, I guess that's a 45 and that's more like a, whatever, not quite 90, maybe 110, whatever it is.
In the 90 up.
So that's the advanced course, right? And remember, we got any number of guys in the course, in the club who've solved the advanced course. I haven't, but whatever. So then comes, this is part of then the challenge course. So this started 6 years ago apparently, and no one's conquered it yet. So the advanced course, the challenge course adds this acute angle. It has popsicle sticks or bumps or something. It now has this intersection construct, and it has a gate construct. Sorry?
Also variable logs.
Oh yeah, also the variable blobs, thank you. And the contrast change, and the change in line width. So you can imagine all kinds of different algorithms in here. And the stains, even the stains are of different percentages of black, 20, 40, 60, 80% black. So I wanted to figure it out so that as long as these were the primitives, I wanted to have a kind of a subset of a simple logic that could detect any of these primitives, so that no matter how you organize the primitives, it's going to find its way around, as long as it's a closed course. Okay, and because of that, I didn't want to do what some people have talked about, which is that to just memorize the course and try and do good odometry or something. I didn't want that. That's cheating. I wanted to be able to recognize the primitives and know what they meant and take the right point of view.
Well, that only works if the course is the same every time, right?
Yeah, if you're memorizing an odometry, it only works if the course is the same. But I
assume that this is just an example.
This is just an example.
Yeah, the course would not be the same way every time.
This is the current course, and the thing that I've heard from the club is that we're not going to change the course until somebody conquers this.
And then they'll change it.
And then they'll change it.
What's that?
Are these individual tiles or is it big?
Yeah, this is a 6-foot by 12-foot course, or it's a big piece of paper. I've seen 2 versions of it.
I've never seen the actual course, so I have no idea.
Oh, okay. Oh, I thought.
The one I've seen is
One
the
that's
big
a
piece of
big sheet
paper.
of vinyl?
Okay. There's a box of tiles up on the shelf.
That too. Well, the tiles are for the other two.
For the other two courses.
Okay.
Yeah, they don't have these other challenge.
But see, end of the day, because I want this to be agnostic. So,
And are the stains just places where we spill coffee on?
Yeah, I think so.
No, they're printed on there.
They're strategic stains.
Yes, very.
so I'm not too worried. As you can see, I'm not too worried about the physical part yet, because until I get my simulator working, I don't really care about the physical part. Except that I will tell you that I took some of those sample tiles in a webcam, and I actually did experiment with that vision algorithm and perspective. So I did enough with the real world camera and a real world tile to see that it should work. Some twiddling and adaptations may be needed, but
But you make no other assumptions about the shape of the course?
no, I don't care how long it is. I don't care how many times these primitives appear. The only thing I care about is that,
Do you care which direction you go on the course?
no. No.
One exception,
You do have that
Which one,
gate,
which one
the
exception?
loop.
the gate.
The
Yeah,
gate?
you're cheating a little there. That's okay.
How am I cheating?
Well, it's a loop technically, right? And really, with a narrow field of view, you might have to pre-memorize which way you were going to go. Otherwise, shouldn't you be looking at that loop?
Well, but for this,
Saying,
okay.
you need a larger perspective on the
No.
course.
The robot should leave gate on branch C.
Oh.
So the primitive is hard-coded to go this one direction.
Oh, boy, read the instructions. Got me
Read the
there.
instruction manual.
Gee,
Of all else
that's something
fails.
I usually don't do.
So-
Poor comprehension.
So if you want to go change the instructions, fine. I'll go change
All right,
my logic.
Carl, very good.
But
Boy.
to finish up on this topic then, so Dave, this part of the node code that I have, the figure out what those lines mean logic, I'm actually trying to borrow from something I learned from you, which is the subsumption architecture. So buried in, and I wasn't going to get into this because it's one of the parts that's least done yet, But the conceptual plan that I have is that I have a bunch of different detectors. I have a detector that knows how to recognize a gate, no matter what the orientation is. I have a detector that knows how to write intersections. That's the only detector I've written so far, is the one that knows how to find. So all that example I gave you of it getting around the course as it is, the only detector that's running is the one that knows how to find intersections. And that's why when it comes to this gate, it tends to go straight through, because these look like an intersection, so it throws them away.
Well, if your field of view is not big enough to,
See the whole loop.
encompass the loop, then
Yeah.
there's no other way to do it, right? I mean,
Well, you could do it the cheese thing, right? The maze where you have to drive around and figure it out, build an image of the map in your brain, and then,
And then run it.
yeah, and that's when I show this to like some of the other meetups I mentioned. I show this to those guys. That's what they assume is going on. Is that to get to that loop, you've got to have a loop detection, and then you can go back. And I'm saying, with these rules, it's hard coded, starting off this way. So ultimately, what I'll have is, and Dave, there's your subscription architecture, if I understand it right. I'll have all these detectors for the ones that are the minimally sufficient set to recognize these different elements: left turn, right turn, S-curve, notch. I'll have these different detectors, okay? And then I'm running them in a chain, and then each detector kind of declares a probability for how accurate. So like right now, the intersection will say, yeah, this is probably an intersection with 80% confidence. So I have some arbitrary metric that says, yeah, that's probably a gate with 60. So it'll run through all these different detectors, pick the one that's most likely, and life goes on. So I have that structure in there, but right now, there's just one detector, and it's the intersection detector. And we can show you how that works. So that's what I'll say on that. So if we visit back here, and all that edge detection, that subsumption architecture, all that logic is buried in this mess right here.
Does it complicate it if you, instead of doing edge detection to compensate for the, white on black, black on white, can you, it's pretty easy to invert an image. And doesn't OpenCV really want?
Yeah, it likes white on black.
Yeah.
It likes white on black. Well, we
Right.
can step through the algorithm here
Yeah.
in a minute. It likes white on black.
Right.
Yeah, but
Are you thinking,
but the thing is that if this is very idealistic, right?
Mm-hmm.
Right now it's showing what happens if you have. Let's go back to this view, and let's turn it on. What happens if we go back to here, and let's say it's offset, or let's say that it's got let's say that this tile up here suddenly changes contrast. So at what point do I have this algorithm flip from the one contrast to another, right?
When it's like
So many percent.
so much percent black.
Yeah.
or region?
And what happens if it's at an angle? I mean, conceptually to me, it started to feel like it was going to get really complicated to have these two modes and have to switch between modes.
Yeah.
So I consciously went towards, let's just walk through it now. I consciously went through this script right here, which starts off with this image, and from here to here, you can see it raises the intensity value to the power of a half. So that tends to do something. And then I get rid of this artifact around the border. I don't know where that comes from. I don't care. Then this next one does a histogram, and it flips the contrast.
Okay.
So there's the white on black that it likes. And then this next one, it doesn't look like it does much here, but on some of these where there's a lot of noise, this is a population threshold. So it says, you're just a little boat on town with 2 or 3 pixels. I'm going to throw you away. You're a megalopolis. I'm going to keep you. So that's what this one does right here. And then this next one, like if we go to 8.5, I think that shows, yeah, so there's population threshold. Now this next one is interesting. It's a close. So what it does is it detects blobs, it grows them until they touch, and then it pulls them back until just before they separate. That's closed from there to there. And you can see, just as I flip through these scripts, right, how easy it is to do in RoboRealm, because you can just open up the dialog for this and change the settings. Okay, what kind of kernel do you want to use? Do you only want to look at both directions, or are you only looking for horizontal things or vertical things? So you can just quickly change the settings on that filter, and you've got the instant response. And then this next one, I think this is it's a common thing within computer vision, but it's not an OpenCV primitive, but it's a primitive in RoboRealm. It's called skeleton. So it attempts to draw a line down the middle of blobs. Now, to you and I, that looks like a single line. Let's look at a more interesting thing. Let's go to waypoint 3. All right. To you and I, what does that look like? That looks like two lines that cross. But to the computer, that's one line. That's one line. So what am I going to do with that? Well, I got to break it up. So let's actually back up a little bit. And you can see my, okay, so now, first thing we do is this next one, and it doesn't even matter, it can be offset, it can have angles, doesn't care. All right, so this next line, this next primitive here, what it does is it says, all right, let's look for things that look like corners of lines. All right, there's one right there. And again, that's a really simple primitive. It's got, I can plot a different kind of cursor on the display to see what it's doing. You can set different parameters for how it detects a corner based on the relative to the number of pixels. And then, let's see, then I have a small JavaScript program. It's a little helper function that prepares an array. And what the array does is it says, okay, for every intersection point, I'm going to add a radius. And that's all the JavaScript program does. And it's kind of nice because you can use, if you don't like JavaScript, you can use Visual Basic or Python or whatever, but you can see it's just a nice simple bit of code right there. And then now after I form that, I take the array of intersections, xy, and now I turn it into xy radius. Then I can plot a circle. Okay, now I have a circle at every intersection. And you can see that if we jump over to, for example, waypoint 9, there should be multiple intersections. Okay? So, multiple intersections, so that means there's going to be multiple lines. And now, then what happens, so this is what it looks like. This is that single line, to us maybe, but to the computer it's a single line. And the green points represent the intersections. And now the circles are plotted at each intersection. So the next part, and this is a cool thing with computer vision, what happens if you subtract this image from that image? So let's take this minus this. What do you get?
Line segments.
Line segments. Right? So you take this minus this, and you get line segments. So the colored stuff is annotations for humans. The white is what the computer's looking at. So now then there's another module. You can just put it in a script, and it says, all right, now take individual lines and sample them every so often and plot a red X. So now we have a case where we have, in view, we have 1, 2, 3, 4, 5 lines. And we have an array of lines. And if we go back to waypoint 0, right, okay, that's interesting because it's not reset, but let's reset it. Let's see how I do this. Stop it, go back here, reset. All right, I'm all out of whack. I don't know how to drive it, but the point is, it's that Y again. You get an array of lines, and that's all that this script does. And you can see down here in the corner, it's running at 20 or 30 hertz right now. So it does from here to all these things I just showed you, it's doing that at like 20 or 30 hertz. Pretty reasonable. So, so now we have these red X's, which are the candidate lines, right? Again, this is just image processing. All we have is a bunch of lines. Now we have to figure out what to do with it. So now, and that's what I've shown you in script form. What's on this page? You start here, and then you wind up with this, and it's just an array of xy coordinates. xy, 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 -1 says it's a new line, xy, xy, xy. So here we have 4 lines, and because all I have so far is the intersection detector, if we go back to that point, I might have to reset it, but normally, Gadzooks.
Carl, you were mentioning
I'll
the
reset it.
rate at which it runs. Does it run multiple cores or threads or one?
We're going to come back to that. That is critical to this whole discussion.
Okay.
That has been the joyous part of my life for the last couple of years.
Charlie, yes,
No, I'm just talking about RoboRealm.
Yes, RoboRealm can handle multiple cores.
Okay,
No, at the moment with the version I have, it doesn't.
okay.
And Node is actually single-threaded as well, but Windows is multiple-threaded.
Yes.
We're going to get back to this.
Okay.
So here you can see, I have something offset, don't I?
So-
Time-wise.
Is that like an i7 that's running, you know?
Oh, that's because we're in the wrong part of the
gigahertz or something?
code. This is an i5.
Oh, okay.
It's an i5, 16 gig of RAM, and it has a SSD. But here you can see that, like if we go over here, you'll see that there is 4 lines. And okay, so the way the thing works is and I told you this is the nose of the robot right about here. So the algorithm looks for lines that are closest to the nose of the robot. It prefers those. And then it also looks for lines that are within about 45 degrees of normal so far, first detector. And if it finds one of those lines, then the intersection detector says, okay, since the closest line to the nose of the robot is within 45 degrees, and that's the best looking line, that's probably a really good line. Given that line, let's look at all the other lines. And it says, well, that's pretty close to the nose of the robot, but it's 90 degrees away. It's an intersection, ignore it. 90 degrees away, ignore it. This one, oh, it's the right number of degrees. I haven't added this. It should say, oh yeah, and its tail is so close to the head of the other one. So that must be an intersection. We're going to ignore these 2 lines and pick this one as the place to go. And that's how right now it's able to pick that line, even though it's seen 5 segments, I think, because it sees this as a line off to the side probably too.
So how does that respond when it gets to a real live 90-degree turn?
Well, again, if you look at the primitives and if you look at the way the course is, the real live 90 degrees, it's all of the examples in here of real live 90 degrees have no other clutter around them. So what I have to do is I have to have the intersection detector, and I have to have a right 90 degree and a left 90 degree detector. Because this is computer vision, so even if this is an angle, it can measure this angle here, right? Between these 2 lines.
Yeah.
I see, so it can't throw away that one because there actually is another straight line that it can prefer.
In this case, it can. Yeah. And then you get into other interesting cases, like if we go to waypoint 1, so let's just let it rip for a little bit here. Except this is now one of the issues that I have to solve, so let's ease into it. Still have some timing things to deal with. But you can see as we get closer to this acute angle, somewhere in here, sometimes it has a little bit of a nub that projects beyond, and it's just an artifact of the way the skeleton, right there. So that's an artifact of the way the skeleton process works. That thing right there. So, I'm going to have to probably deal with that somehow.
Because that one line would seem preferable because it's
In the right direction.
Depending on how I write the subsumption architecture detectors. Yes. So, but that's just straight logic part. That I think that's just geometry.
And it
right?
is terminating somewhere in the center of the field of view, not near an edge.
Well, the
Is
control
that-
loop, the control loop is always driving towards the point of the yellow arrow. And right now it's a very simple control loop. There's no PID, there's no nothing. It just says, oh, that's the. Actually,
Just
it's, what is it, a second order or something, because it's gonna take, if the error signal is over here, it's gonna take like 80 or 90% of the angle and 80 or 90% of the distance. And that'll be the error command to feed in. But there's no other fancy math at the moment. That's to be done later.
No, but I was just saying, although maybe it doesn't make sense, but if you were to progress that short segment, it's like, it wouldn't go anywhere.
Yeah, if we keep going,
You're in the
it-
middle of the screen,
yeah.
you're not running off the edge of the
Yeah,
field of view, right?
So you can see just between these, and now, okay, I have some funky logic in there. If I go there, then it's gonna get lost, because I have a kind of a gate function really close to the nose. So again, it's a matter of, cleaning up
Maybe just two.
the acute angle detector in this assumption architecture. So the acute angle detector is going to have some squirrely logic so that it can handle all these different orientations. You know, it's not going to be perfect, so it's going to come in at off center, and it's going to be all messed up in ways, new and exciting ways. So yeah, so that's you've seen the simulator now that returns an image, and then you've seen the vision processing part that says, okay, here's an array of lines. We're going to send that to the robot controller, and then in that robot controller, we've talked about it. I wasn't really planning to, so I don't have any slides, but there's a lot going on in here. But it's just tedious math. Look for these things if you see that. Look for these angles if you see that. If you have this known line here, then look for these other lines. So it's just tedium. I think the right angle detector took about 4 hours, if I remember right.
It would be cool to see, maybe you mentioned this, I'm stupid, but it would be cool to see, based on your simulation, you know, what the route was that was taken. That way you could
Yeah.
look at a glance, you'd see.
Oh, yeah.
Look,
Absolutely.
Did it perfectly without having to really follow it or say.
So
oh,
there is
that's-
there is a part of this logic which I have in my. I'm going to talk about technical debt in a little while, but part of the technical debt I've built up is a cookie trail of where it's been.
Ah,
So right now since it's simulator mode and it's easy to regenerate, I'm only building an array that has the XY thetas. So I have an array of every one of these that it's visited since I hit reset.
And that's updated at whatever the 20 hertz.
Doesn't matter, yeah. And the 20 hertz is just what it happens to be, because it's going as fast as it can. So like right now with screen share on, it's actually slowing down my computer, and it's slowing down the simulation.
Yeah. Of course.
But yeah, so as fast as it can go, it builds that array up. Ultimately, I think it'd be really cool if I could not only have that array in memory, but write it to a Mongo database, and actually be able to write a JPEG of the image, or a compressed version of the image.
Yeah.
Because then, you know, for all the pain that it is to set up this course, whatever it looks like, I can go run the course once, and if it starts to get stuck in the real world, then I can always go back and then look at that section, that image, and say, no, why did my algorithm fail on that exact snapshot? And of course, it wouldn't work the same as the simulator, because the image is situation dependent, but at least for that one image, that one point in time,
Yeah.
it's
cool.
repeatable. It's
Scroll
repeatable.
through the whole history, just
Yeah,
back and forth.
exactly.
Yeah, anyway.
Like I said, there's so many directions that this could go, right? But it's been a really good learning experience.
2 years of scope creep.
2 years of scope creep, thank you. That's a good way to view it. So and then, what a segue, right? So interesting findings, because there's a lot of learning along the way. And so just out of curiosity, how many people have played with Node or JavaScript? Good. Okay, a few. Good. So you guys will keep me honest, because I've just taught
Well,
myself.
I've written 10 lines of JavaScript.
Yeah. Well, yeah.
That's how it starts, isn't it?
Like a PayPal shopping cart thing, I think.
You know, that's how it starts.
Okay.
And I figured based on some success with the 10-line thing that this is just difference from 10 lines to 100 lines, no different.
1,000 hours.
Gadzooks. That's exactly right. Okay, so first thing for those that might not know, Java is not JavaScript. They're just two different beasts, completely two different beasts. Okay, next thing that's interesting is that it's an ideal language and it's evolving, it's continuing to evolve, it keeps changing. And it's used in a lot of places. It's used in a browser. So the same JavaScript might run the same or it might run differently if it's in the browser versus Node.js. There's actually a flavor of it that's meant for IoT, so this runs JavaScript. You know, on a hearing aid battery, right? So it doesn't even have to consume a lot of power. There's a Bluetooth beacon with some sensors in it, and it's got a switch. And if you take it apart, you can wire into some GPIO. So there's a lot. There's some interesting stuff out there. You can run it in Azure or Amazon Web or the cloud. There's a flavor of it Facebook started that makes native apps for iOS and Android. There's a flavor of it, Electron, that you can run apps for Windows or Linux or Macs. And there's bits and pieces of it in RoboRealm. There's a thing called Node-RED that's kind of cool. And what's neat about it is that it's a pretty high level, pretty abstract language, and it's really flexible. And what's painful about it is that it's really flexible, and it's a pretty abstract language. And its behavior can vary a lot if you don't know what's going on in the environment that it's running in. So that gets to the journey here. So I started off around mid-2015. I didn't know what to ask, what to look for. Then I saw things, I didn't understand what was going on. And when I finally saw it I didn't understand, then I didn't know how to fix it. But damn it, this thing was going to keep going on. So I kept going and I started to build up this technical debt. So I had bad design patterns. And after 2 years, this was taking us to May in our club presentation, our club competition in May this year, 2017. And if you remember, it was moving around the course, but it was really slow and jerky. And that was because I had all these hard-coded timings. There was a fundamental thing I didn't understand, and I had hacked around it in every piece of my code with hard-coded timings. And that meant that the first time I tried to do a web share, the system tasks were much slower than I'd been used to, and it just totally broke right away. It wouldn't run at all. Whereas now, today, it's actually running pretty well. Because in the last few months, I've figured out a lot of code rewriting, and I've figured out more proper patterns. And there's something called the node event loop. And so I've gone from hard-coded timings to consciously scheduling events one after another in the right sequence, and I figured out how to do that. So we went from the project used to work despite the way that it was written, to now it works because of the way it's written. And there's still some cleanup I got to do, but I'm really hopeful that by November, I'll be having this thing march around the virtual course. At least the simplified version, hopefully the real version with the contrast changes. And then sometime next year, I'll hook it up to a real physical platform.
So you're event driven, and so you don't have a periodic clock or a periodic
Correct.
event type of thing?
Correct.
Okay.
Does anybody not know what event driven means?
It's just asynchronous, whatever
Yeah.
happens.
Yeah, so that's a great segue. Okay, so we're going to come back to the event loop in a minute, but I'll show you by way of code demo what can happen. So I have a, it's pretty small, isn't it?
Yeah.
Okay, I couldn't figure out how to get my ID much bigger, so.
Text up there?
Huh?
I said, oh, is that text up there?
So,
It's an eye chart.
So, and I have this repo that there's a GitHub I'll share afterwards. But let's say that there's this one function right here. I'll uncomment it, And all it has to do is wait 6 seconds and then write the name of the program. So we'll go 1001, 1002, 1003, 1004, 1005, 1006. Simple, right? And that line is right there. Now let's say we have another one that comes after it. We'll just see how that one works by itself. And all it has to do is wait 4 seconds. So we go 1001, 1002, 3, 1004, 1000. Perfect, right? So now what happens if we try and do them in order? Anybody want to predict what's going to happen? So remember, the first one writes program 1, the second one writes program 2. Foobar 1, Foobar 2. So we'll go
Second one.
1001, 1002, 1003, 1004, what?
And then-
Wait a second. It was supposed to wait 6 seconds and then write 1 and then wait 4 seconds and write 2. But instead, right, watch it. After 4 seconds, it executes this line, and then a couple seconds later, it executes this one. Well, what the?
That's what it ought to-
Blocking.
That's what it ought to do.
Yeah, it's what it should do.
It's Windows.
It was very confusing to me for a long time. And that meant that, if you went on and had like a for loop, right? So let's say we have a for loop, and we want to do, increment from 1 to 10 and then just bump a counter. Well, let's say that task that's going on is that we want it to wait a second and a half and then bump the counter. Wait a second and a half, bump the counter. So when I first did a for loop, I thought this would be natural, right? For 1 to 10, we're going to wait a second and a half, bump the counter, and then we'll wait another second and a half. But if I do this, all of a sudden,
Everything comes out of it.
everything's at once.
Yeah.
So this was the great mystery to me for quite some time in terms of how do I deal with it, right? So, because Node is synchronous, JavaScript's synchronous, but Node is asynchronous. So what the hell's going on? So after I learned a little bit, now there's another style. I won't get into the details right off the bat, but let's say we do node aha.js. So now here's that first function. It waits 6 seconds and plots out.
You need to have that schedule the next, right? If you want.
Yep. So now same thing. So now these two lines behave the same, whereas 2 comes out before 1 because we asked it to. Now let's say we comment those out. Let's say we use this thing called promises. And what the promises do is, now that's the way where you can tell Node that these should be going in a sequence. And it'll say, okay, first execute the one that writes out the 1, and then execute the one that writes out a 2. So this simple syntax change, or grammar, or whatever it is, now it'll wait 6 seconds and write the 1, and then after 4 more seconds, it'll write the 2. So that's the real simple pattern, and all it took was to understand that as Node flies through this code, it's evaluating this stuff. It's putting the evaluated stuff to some queue, some event queue. If it's synchronous code, I think it'll execute it right away. If it's something that's going to take a while, like a wait command has a timer, it's going to schedule that for evaluation on the next turn of the event loop. So that's jumping into the next part here, the event loop. Like I said, I warned you ahead of time, this is going to bounce around a bit. So what's going on is that Node has this event loop, single thread. So it'll go and it'll process, to my understanding, it'll process line by line in sequence. But if one of those lines is like a timer or a file system write or a go check this from the socket out on the internet, then it's going to spool that off to some non-blocking worker thread. It'll let the OS handle a new thread, and it'll handle that off to the side, and then it'll keep on chugging along with the loop. So it'll say, so on our example there, it said, okay, wait 6 seconds, then write. Well, that's a timer. I'm going to queue it off to the side. Wait 4 seconds, and then write. That's a timer. So it'll just keep going through that code, and then after so many milliseconds later, oh yeah, there's a callback. It throws that in the event loop, and it'll execute that callback. So that's how we were doing it with system timers. But the same thing happens if it calls out to some payment processing gateway or Facebook to get the latest image or post. It's the same kind of thing that's going on. Node is just always running, but it's very deferential to these system
And it does
tasks.
that with a callback. So those
Yeah.
look like exceptions or interrupts.
No, callbacks. It's callback based.
Okay.
And then there are other constructs that I think are kind of, to my understanding, they're based on callbacks, but events, event emitters, promises. But I think it kind of boils down to these callbacks in this big long event queue. So it executes what it can. Unless it's long running, then it'll pause that. It'll go check if there's any I/O, and then it'll come back and pick up where it was.
So is this really meant to do, it doesn't sound like it's meant to do sequential type tasks at all, like if you have a web page and it really doesn't matter which things appear, just as long as eventually they all get out there. Isn't it?
That's
more-
your job as the designer.
So you have to worry about whether things have
It
completed.
doesn't sound like it's really
proceed.
geared for that though. I mean,
But it's really, that's the kind of funny, that's the ironic part of it. It's actually very well geared towards it. Because it can, yeah.
It just says, it's up to you to decide how you want it
But even.
and how you code it.
Even in your attempts to do like a for loop, how do you know?
I just didn't know the pattern.
But
Now I
if
know
you-
the patterns,
If you
or
really
some
want to use
patterns.
a for loop, it's gonna do what it did where it spit them all out at once, right?
Well,
No, you put it in a promise.
Yeah, I put it in a promise. Yeah.
Basically, the for loop is just filling up the queue. Just
It's filling up the queue.
Spitting all those things
It's all,
out.
and if they're synchronous tasks, it's gonna do them in order. If there are these things that have to get spun off for I/O, then it's gonna come back to them when it can. It'll queue them all up, and then they'll get done when they're done. So that's that was one of the difficult challenges for me early on, is to figure out, well, what's the difference between a synchronous command and asynchronous command? How do you tell the difference? If you're going, that's why I wrote these samples this way, right? Because there's nothing in here that says this is a synchronous command versus asynchronous.
Mhm.
You just have to know.
You have to check to see if something's done that you are depending on,
In
right?
some ways, there is something there that tells you, which is that there's a wait. And unless you're gonna block for everybody else, the wait pretty much demands you go into a queue.
But
Yes?
yes, but in this case, I mean, how often are you going to go? Let's say you're relying on all these other external libraries. Are you going to go read through and thread through all the external libraries to figure out if there's weights embedded in there?
That would be your job, yeah.
Says the manager.
And that's why for production code, that's what you have to do, right?
Yeah.
Before you rely on a library, you better go through and
Learn about your library.
learn about what you're using. What's inside that magic black box?
Yeah.
So I didn't realize that. Now I do. And now rather than reading the code, at least I can recognize when I see it, and I know how to go deal with it then.
Well, the problem I often run into is that it's actually the opposite, that what's happening down there somewhere in the library is that there's a blocking call. And so while you're assuming that everything's running, you were actually hung down here on somebody spinning on a hardware bit.
Yeah.
You know, it's the opposite problem.
Yeah, it's better to be able to say, is the thing I need done? If not, then go on, right? Yeah.
So I don't have any great, I think Steve has the right answer. Let's say practice, what I've been figuring out is that, go with those better established proven libraries. And what I've found is that you can tell from the documentation and stuff if they're crap written, or at least they have a good attempt at being well written. And the well written ones these days, I think, are very often going to be returning promises. So if it's returning a promise, then you know that they've handled that. They've written it in a good Node style that's not going to block. You got a good chance that that's the case.
He equivocates a little bit.
It's the Wild West. It truly is.
Your mileage may vary.
And don't even get started on variable types, because
That's what testing is for. To figure out the difference between the good and the bad
yeah.
and the ugly.
And the ugly.
Darn.
But to Ray's question on how do you do a for loop then? Well, so let me see. I have a version of that actually. Where's that version?
It's not-
Our variable types dynamic, is that what you're gonna tell us? You can change types around.
Yeah, I wasn't even gonna go there,
Okay.
because
I figured it was.
there's some crazy stuff. Where did I write this? Anyhow, yeah, there's ways to do it, and it involves like the for loop recursion, and there's some other ways too, but I think, but I don't think I have one here after all.
If your for loop doesn't have any wait states in it, any wait commands, is there any problem with the for loop?
Not your grandfather's
Well-
for loop, I guess.
No. If they're all synchronous, if they're all those kind of commands that can be evaluated and return a value immediately, then you should be fine. If any of those for statements are the kind that say, well, let's go read time and temperature.gov, then that involves I/O, system I/O. So it's going to be executed, but that's all that's going to do is say for 1 to 10, queue a read of time and temperature in sequence as fast as you can do it. Queue them up, and then it'll queue. If you have a 1 to 10, go fetch time and temp.gov. It's going to queue up 10 in a row. They're going to go out, if your system can handle it, it's going to spin up 10 independent requests at the same time, and you're going to get 10 responses at the same time.
So yeah, you're not allowed to block, you can't
I
say,
don't
go fetch
understand
time
the
and temperature.
problem you're having, to me, it makes,
Well,
everything
because
makes sense.
you're thinking
It's
in,
an event-driven program. When you tell it wait,
You
it
don't.
goes about its business.
If you tell it wait, but if
It
you're
goes about its business
yeah.
until that event occurs. When that event occurs, it happens. I mean, to me, that's straightforward.
but there's
And
not
that-
really an explicit wait where you could say, go get the time and temperature and don't do anything else till it's
well,
back.
it's not a pause, it's just wait so many, I mean, you know,
Waits for the callback.
wait for the callback. So I don't understand.
But the for loop doesn't do that.
Huh?
The for
doesn't
loop,
do it.
the for loop doesn't wait for a callback.
Well,
For
I'm
loop.
saying when you say,
Can you explicitly wait for the
when
callback?
you don't really,
But
it's
even
not
if
a
you did,
pause.
that
You're
wait
not pausing the
is stuck in the queue.
program,
You haven't
you're
got
just
it.
saying wait before
Right.
this action
Well,
takes place.
I guess the
So
question-
to me, that's straightforward. In fact, my problem is how in the heck to do that, because that's what you want for subsumption architecture. The subsumption architecture wants to respond to events.
Yep.
And it wants, and it don't care when or how, you know, it just has this bunch of events. When this event occurs, it does this, and there's no order or sequence.
Well, that's part of the design patterns for this language and environment is to draft it in a way so that they happen in whatever order they're asynchronous. They happen as they will, but you can say they're like this promise has actually got an internal state machine, so it can only be resolved state or a couple others, or unresolved state or rejected state. So any one of these things can transition the state machine, and so the bottom line is, you can say is that okay, I'm going to spin up all these tasks, and then when they all return a value or timeout, I will resolve the union of those tasks.
Well, go ahead.
And that's just part of the coding. It's part of the design pattern that you have to learn.
So just
Took
throw
me-
all your statements out there randomly and figure it out.
Yeah, and that's.
Sort it out afterwards.
Did I mention I've been rewriting for a couple months now? So,
Wow.
yes, technical debt. So anyhow, so it's kind of fun to play with, but it just looks really powerful in the way that you can do a lot of stuff with it. I've along the way picked up quite a few things. I'm no expert, but I'm learning a lot about best practices, and I got a bunch of resources to share. I've learned a lot about Git, so code bases in code version control with Git, Node.js, computer vision, design patterns, object-oriented stuff. I didn't really touch on that, but API design. I don't know how many IDEs are out there. I've played with a few of them, but yeah. sockets and XML, so the interface from Node to RoboRealm is actually, I had to figure out sockets and XML. That wasn't pretty. And then just mixing around with different people was pretty good. And then, anyhow, this will be in the notes, but if you wanted to play with the examples I have, you can go here. I got a whole bunch of pages of slides. These meetups have been useful for various purposes. People that are doing similar things or related things. And then there's just a bunch of links for books and things on JavaScript and Node. And some training. So there we go. That's flying through. I don't know if I've answered all the comments or questions, but.
Well, I have a lot more. I'd like to go back to just conceptually how you're solving the larger problem.
Okay.
With a couple of questions based on the description of your algorithm. How will you approach if you actually lose the line totally?
Yeah. So.
What happens if you totally lose the line?
So somewhere there's a little evidence of this. Darn little, but.
Your robot ate the red pill, I guess.
So somewhere, like, I have this idea, and this part isn't written, so I'm going to tell you about the approach I have in mind, but it's not written yet. So somewhere I have in mind, there's a bunch of little state machines in this logic, right? At the highest level, I envision a state machine. I have it sketched out somewhere. I could probably find it in my code repo. But somewhere I have in mind a state machine that, actually let me pull it up, because I think I know where it is.
You do like the Rama does and go in wider and wider circles.
Well,
Yeah, but that's-
that would be a separate behavior. Though.
A separate state. So here in my repo,
It's the
I
red pill
have,
reality.
what's the name of this?
Something different, you no longer.
It might be the default.
Give me a moment, Dave, I'll answer that for you. Analysis, this one is data, just a second. Here we go, this is it. Pretty sure. Yeah, so these were back from June of 2015.
So it's one of those be perceived as an object. It's kind of off. Okay. It's the
What modes? All right.
It really is sketched out.
It was actually there.
We have a different use of that word now.
Yeah, yeah, I know it. But here, so at the highest level, I'll have a bunch of modes or states, right? There'll be a power on test. It'll check the sensors, actuators. Maybe it'll do algorithm, it'll do a perspective measurement, right? And it'll say, well, this is the correction, I need to square that up. Because today the image is at this angle versus the other day it was at that
Camera
image.
moved.
Yeah, so there'll be some power on stuff. There'll be a find the course mode. There'll be a hey, I'm on course mode. There'll be a hey, I'm lost mode, or I'm off the course and I think I can get back on. So I envision that and then there's a kind of a progress status. So ultimately, if we know the course ahead of time and we know that there's going to be like one gate, or we know there's going to be one big jump, I could have some estimate that says, yeah, well, I've cleared that marker, got that waypoint, and I could tick off some estimate of where I am on the course, just being told about what the course is like.
Yes, Pat, your step number 2 there, find the course. That suggests that you could just put the robot down arbitrarily anywhere.
Yeah, that's my intention.
It doesn't have to.
It'll go
be
look for a
set
line.
down, and you don't have to tell it what its X, Y, and theta are. It's
Right.
initial.
Yeah,
It's you wander around, find the course, and orient yourself.
yeah.
Yeah, very cool.
That's the idea. I mean, why would I start this on the start? I'll start this off the side. I'll go find the course,
Put it out in the middle of the
and then
course.
turn right. Because on this course, it's intended to go counterclockwise.
That's why I was asking if you could go either direction.
Well, I could, but the course says go right, counterclockwise. So.
Keep to the right.
But yeah, that's exactly the idea. So I have that planned. And then I figure there'll be these services running in the background. There's like calibrate video, there's assess where we are on the track, there's monitor the health, so looking at the battery, the current, frames per second on the videos, just some kind of health monitoring. Then the video, it worked out differently than this, but, and then this is pretty much the same. Determine a targeting aim point, determine a move command, issue the command, verify that it got acted on. And then this is some like representation of the robot base. Is it 2 wheels or is it omni-wheel?
Is that a collection of napkins?
Yeah.
Or envelopes.
I use 8.5 by 11 napkins,
Oh, yeah.
but this was notes from the discussion with Steve. So here, you even got your name in infamy there, Steve. May 19, we had this talk, and you were helping me out with tools and such. So
That could be subpoenaed, for example.
That's right.
And this is the top level plan, right? You got a camera, other sensors, you've got motion, other actuators, and in between is magic.
Which you've been working on for 2 years.
That's my plan.
He's working on the magic.
Navigate them, robot them. Okay. So anyhow, what other questions you got, Dave? Because I know you have a bunch.
That actually answered quite a bit right there.
Okay.
Yeah, just sort of the overall strategy and how you're.
And it's a strategy. I mean, it's taking form, right? What's kind of cool is that if I showed, I gave an earlier version of this back in the DPRG in April of 2016. So that was a year into it. And, I wanted to be the first to do it. None of you guys are taking me on, so you're giving me all this time. I'm just filling the time because nobody's trying to beat me to it. But, get current on software, learn machine vision. Unique solution, I think it's unique, learn embedded. So, there's the approach, discrete, event-driven, most of the brains on the laptop, yep, that's the same. The layout is very much the same, so.
And what will be your link, a comm link to the actual physical road?
So, there will be multiple links.
Multiple links?
Yes, multiple links. So here's the simulator version, right? So right now you've got this local port for, this web page has got its own node service to serve the web page. Then that web page talks to the node service that I just talked about today. And it has Node and Express. I don't yet have the Mongo piece to track history, but at some point. So that's HTTP and JSON. And then there's the XML sockets interface to RoboRealm. And you said, how's it work with the robot? Well, if we replace the simulator with the real robot, where'd it go? Then we're still going to have this service to these 4 buttons and that link to the node. But now we're going to have telemetry and control over Wi-Fi, and then the webcam. I'm going to have the phone on the robot streaming the webcam over to the laptop where this part lives. So this part here with Node and the RoboRealm will be at Windows on a laptop. And then the platform will just have wheels, motors, and a Wi-Fi and a webcam stream. Literally, this iPhone can stream into RoboRealm video. So I don't have to worry about drivers at that level, but it's been enough to mess with drivers at some level. But yeah, so the same, this whole framework you could see from a year ago, it's taken form, it's getting there.
Is the Wi-Fi link going to be two-way or just one way? You're telling the robot to turn left, right, speed up, slow down, or is there going to be some sort of a closed loop?
I'm sure. I want it to be closed loop because, like, if we think about where did that go? Where did that go? Here. I think it's here. Yeah. So if we think about, like, now we're getting into this layer. So the real world, the difference between the simulated robot and the real robot. Well, in the simulated robot, like I mentioned, the move commands are given in a number of pixels or a number of degrees to turn. So if a real robot has encoders, if the platform happens to have encoders, then I can, instead of giving pixels, I can give it encoder ticks, right? So I can have it be discrete that way. Or I figure another kind of robot might just respond to impulse response. So maybe it has a finite impulse response filter, and I'll just instead of giving a specific number of encoders ticks to go, I'll just say, okay, do an impulse this big of this duration, and then that'll translate into some wheel movement, and then with a finite response, it'll turn the wheels off and wait for the next impulse. So that's an abstraction layer thing that
Ask in your simulation, do you keep track of the absolute orientation of the robot?
Yeah. Well, the simulator knows. The simulator knows the X, Y, and the orientation on the course. The robot doesn't. Because I have to assume the robot only knows what it can see, and in this case, it can only see 160 by 120. Yeah. So you don't.
My question is basically, the reason for my question is, you, at least I assume what you need to know is that your image orientation in global terms,
Yeah.
not with respect to the robot. But your camera is going to be mounted on the robot.
Yeah.
So in order to know the image orientation in global coordinates, you're going to have to know the robot orientation in global coordinates. And so I'm asking, do you keep, in your simulation, do you keep track of the orientation of the robot?
Absolutely.
Do you have?
That's this piece right here, the simulator. So, like if we look at this block diagram, the
Do you care about?
Yeah, can it be relative?
Wait a minute.
Yeah.
well,
If you're
who
studying
cares?
the images,
Who cares is the
you're
question,
making-
right?
you're
So
making
here's the
decisions.
thing. If you look at the simulator in RoboRealm, this knows where the robot is at any given time. This piece
Well,
of
when you
code.
say where it knows where it is, are you saying it knows the X, Y, and theta?
Yes. With respect, okay, so this, remember, in the simulator, the virtual course is nothing more than a JPEG or PNG
Right.
of so many pixels by so many pixels. So literally, the XY is the XY number of pixels, and the orientation is the number of degrees from 90 or whatever. And this simulator that's in RoboRealm, it knows, this one right here, it knows at any given time, in global coordinates of pixels to that coarse image that the simulator has, it knows where the robot is.
Okay.
But the robot has no idea
But
itself.
you're not using that information when you're making the robot move.
The robot is not using that information.
Right, all that's
It's just making
being
a decision,
used
saying I
for
need to
is
turn
what's the
30
image.
degrees. I don't care which way I'm facing. It might be nice to know, but you don't care because you're looking at the picture.
Do you care whether your image is rotated?
No, that's another question. I wasn't sure. Now that I see where you're going. So, and that's what's cool. That's what's cool about computer vision is that you can see that this arrow. So no matter how I turn this until I get outside of my 45-degree rule, it's still finding that line. And the same is, okay, a better example is the intersection. So if we go to this intersection, so intersection is looking for 90-degree things, right? In the image processing, it doesn't care what orientation it is. It still knows that that's, now it thinks that this is the closest line and it should go through the intersection that way.
That's
Because
because
it
the
got
simulator always assumes the robot's in that bottom center.
Yeah.
You-
And I assume that I'm gonna tend to keep the line within some proximity of 45.
Yeah.
If it's out of 45, then I'm gonna say I'm either lost or I have to go figure out which one to take again.
I believe you said you've only programmed
One detector.
one detector. So I guess my question is, you haven't done it yet, but what are you gonna do on the gap?
On the gap, well, that's a great question. And let's say that we're at the gap. Actually, how do we get to the gap? I think it's over here. Nope, it's over here. Somewhere here. There's the gap. So, with this relative number of pixels to size of the course, there won't be much of the gap visible. And so I presume that part of that outer state machine that says, am I lost or am I on course, it's gonna, I believe that the detector will say, well, I'm following along in this line, then all of a sudden, I don't see any lines that are anywhere close. So I'm gonna just keep going for at least so far and see if I can pick up a line. I'm gonna go straight as much as I can and see if I can pick up what looks like continue. So that's one way to do it. The other way is that if the field of view is big enough to see both elements, then I can look for a line that's of the same orientation, same line with so much of a gap.
Is
in
there
it.
just one gap?
Yeah, that, on this course, it's only once.
One?
Well, you got the little gaps with the S-shaped thing.
Yeah, but I have a
No,
different
I'm
approach
talking
for
about a
those.
big gap. And let's see, which way are we going with that and that?
Well, you got a
Left.
little segment on the left there.
This way, to the,
Confused.
We're going,
from the middle of the course towards the edge of the course.
okay, so basically, how much of a straight line? In other words, to me, it sounds like the only way you're gonna be able to handle the gap is you've got to know the orientation of that little straight line heading into the gap.
And I know it.
Okay.
Already, every one of these lines, every 20 hertz or however fast my program is picking it up, it is
Do you know it in global coordinates or in robot coordinates?
robot. But that's all I care about.
May I stick my big nose in here?
Go ahead.
This may not be the question that's being asked here, but I think what it falls down to is that there's a translation between pixels and ticks, encoder ticks. And the encoder ticks by themselves actually don't give you the information. You have to process those and get an X, Y, and theta out of them. And the X, Y, and theta that you're describing is actually based on pixels rather than based on odometry.
Oh, yeah, absolutely.
So there has to be a translation between
Yeah.
pixels and
Yeah,
odometry.
exactly.
So, and you can think of that like a standard global to local
Transfer function.
transfer.
Well, actually,
Does that answer the question? Is
well,
that- or
actually,
is that
I
on-
don't think you actually are doing any transform in that sense, in that any transforms you're doing only relate to what picture you're going to pick up.
Yeah.
And as far as the motion and the robot and what you're doing,
It's a separate-
it's a completely separate thing. There's no mapping at all.
So really, all
They're
you're
two
saying
different
is,
realms.
do I turn left or right or go straight?
Yes, yes. They're totally different realms. Now, there's the one is, what image am I gonna pick up because of where things really are?
Yep.
And then once I pick up that image, it says, forget about where I am and what orientation I am, where do I go? Two different realms, no mapping.
We could call one of those the robot.
The global realm?
Someone ought to write a program like that.
But I suppose you'd like to know something about that mapping, so you know how to plan the response of your robot, right? So you know, what is it
Why?
gonna take me to turn
Why?
45 degrees? Well, I mean, I'm just thinking if you're limited in your update rates,
We're talking
like you
practical
wanna-
terms to speed it up or tighten it up or reduce the
Yeah,
getting
I
up.
guess maybe that's where I'm.
You don't,
Well,
you don't want the thing to overshoot, right? Because you want the right level balance between.
But
think
you
also
think
based-
you run the right speed
Yeah.
that handles it.
Yeah,
This
just
is
put the right
really
transfer
what I-
function in and you're golden, because the loop will close. Even a stupid simple one like I have. And it really just boils it down to a image analysis problem.
Yeah.
But I guess with that said, sort of an interesting take on this is just how close do you want to be into the problem? Right now, you're pretty close down. But ultimately, you could be there studying it and do your route planning. There's nothing wrong with that, studying that image where you can investigate the image.
Sure.
I guess sequentially, you're gonna execute probably something like this, but you might have a little more freedom to make some determinations about these problems that are in front of you.
Interesting.
So, I mean, because right now, I feel like I have a better chance of seeing what's going on when I can see the whole picture. And you take it down like you're down here, and oh boy, yeah, I'm having to investigate all these complicated rules.
So?
I suspect that with a bird's eye view of the whole thing, I suspect you could cheat a little bit and you could probably find your way around that course with less difficulty.
Isn't that
I
though-
suspect I could
isn't
blur
that
that
against
image
the
right
rules?
now. Oh, am I not allowed to do that?
I don't know.
I have to be
Is
down
the
there.
laptop you're describing going to be on the robot?
No,
So,
doesn't have to be.
So it could be sitting over at the corner of the course, and it could have a big tall camera on it that could see the whole course.
Yeah.
Yeah, I bet you Carl right now could stuff that image into RoboRealm and process it pretty well to where those would all be connected lines, and he probably wouldn't even care in
You know,
a lot of those cases.
we talked about doing that on CAN, where you'd actually have an external camera that could see the whole course and plot where the robots and the cans are, and so forth. And a relatively stupid robot that's really just remotely controlled. But I wasn't sure that was allowable.
Not, can't.
Can't get, but it
Well, we
is.
can have beacons, right? And they can be outside of a.
You can have beacons.
And the camera couldn't be a beacon?
No.
But to get to where I think you're aiming somewhere is that,
But you can't have large orange.
you know, the more of an image you process at once, the more pixels there are, and the slower it gets. And
Okay.
And because there's more information to process, right? You're going to see more line segments. There's just got more math to do. So there's going to be some trade-off between how much you view and how fast it is. And the other thing is that I took the idea, or I had the idea at the start, that if I try and allow the robot to think about too much at once, that it's going to get confused by noise. So I actually had a thought that somewhere in some earlier version of this, I have different masks. And I thought that, well, if it's in this mode while it's on the course, and I know that it's on the line, then I'm just going to neck down to where I'm just a bit bigger than the line, and I'm only going to follow that line. And that'll help me automatically screen out all this other noise that's around it, because I know I'm on the line. Now if one of these detectors say, well, I'm not so sure I'm on the line, then maybe it needs to zoom, reduce the mask and get a larger field of view. But, right, so think about it here. I'm going to take a 1080p, 30 frame per second video stream, and I'm going to neck it down to 160 by 120.
You know, there was I think it was up in Seattle a few years ago, they had a line following contest, but one of the neat things they had was that there was a little demo set up where you turned your back and you had a camera that only saw what the robot saw. So, you know, you can't see the whole course. And you were supposed to try to
Figure out
remote
what to
control
do.
drive the course.
Yeah.
And people were terrible at it.
Yeah.
Because there was no orientation, they couldn't tell where they were.
Yeah.
And the robots were actually much better at it than the people. So it was an interesting thing.
I bet, yeah.
You would think,
Well,
even
that's a
microscopically, they should be able to figure that out.
It's very hard to know where you
data
are.
for telling the robot which way to go.
Remote control cars.
Talk about there.
Yeah.
When you're driving, you're looking down the road and you're getting prior
Oh,
And it was really
data that tells you
what you were looking at.
more or less what you're gonna do when
What
you
the
get
next
there.
move is.
yeah.
Yeah.
The one question I have, for a short time at TI, I worked in a group that did some image tracking. And they talked about blue sky trackers,
Okay.
which meant there was no, all you had out there was blue sky and your target.
Yeah.
And this whole course is, with a very minor exception, is a blue sky course.
Yeah.
Is your approach amenable to where you got a lot of speckles and close lines that come close and that sort of thing?
Well, let's start with speckles, because I think if you look at this right now, you'll see there's a lot of speckles. You got this orange thing, you got this gray stuff, and as you go through it, it's all gone. It just boils it down to 4 lines.
What would happen if a line came close and
So
veered off?
and that does happen now, and that's a matter of me. I think it's just stupid math dialing it in. But if we get, for example, if we get over to point 6 is where it gets confused
The
most.
reason I asked that, I made up a set of tiles that had that kind of problem.
Well, here, this is where it happens, right? This is this
And
part
they
of the
take
course.
over.
If you look at this part of the course, you'll see they're kind of close to each other. Those lines, and if I step at a time, so you can see it jumped
From one line to the
from
other.
one.
Yeah,
So it-
that's a problem.
So I have to see how it did that. So I have
When you say
to.
those are close, I say they're far apart.
Oh, but with respect to your.
From my
current
intersection
location.
finding algorithm, which is the only one I've written so far, they look close. So you see, what I have to do is clean up that, so it's more crisp in terms of this is an intersection or not, or this is the right line to follow or not. Like, so one of the things that I've started to, part of the technical debt I've built up is there is a history of the past line. So it knows from the relative view of the last image what was the angle and position of the last aim point line. So it can compare that to the next aim point line, and it can say, well, you know, if I move just this little bit, the other way was it?
Yeah, why is that?
If I move just this little bit, you know, why does it prefer suddenly this line over that? Because this other line was much closer to the prior line. And I don't have that prior line comparison logic built in yet.
Oh,
If I did, then I could make it prefer lines, not just the lines that are closest to the nose, but also lines that were closest to the most recent one we were on.
But I thought you assumed your snout was right where your cursor
The
is.
snout is right there.
Right, so in that case, shouldn't you pick up that other line? Or you say you're not doing
I
that,
think it may be, let's see.
It probably lies the right hand.
right? Because your
I
nose is.
don't know. I would have to go turn on the debug for that math part and look at it. And I'm sure that if we looked at it, you would see that it's because some tolerance that I have somewhere, that it doesn't yet handle this part very well. But I mean, literally, there was one afternoon when
This is like, so in that case, if you do a minimum distance between where your nose is, center of the bottom of the screen, you should pick up that other edge or that other set of points.
Yeah.
Okay, well, that would be.
Except when there's a gap and you don't have the line.
You don't have, then you need to know where you were and,
Right.
and how long to continue trying.
Yeah.
So it's not exactly that continuous integration test-driven design that Steve wants me to do.
We're working him towards that direction.
But in terms of this manual test-driven design, it's very much like that. But it's repeatable. The simulator is very repeatable. So
Is the reason it's having trouble with those 90-degree turns because at that point it's fallen outside of the
I think so.
acceptable 45-degree?
yeah, I think so. And I think I have error. There was some weak attempt to get the comparison to the prior angle in there, but I'm quite sure that I have logical error and such. That's when I said this timing interaction, I really have to get the event loop under control.
Well, it could clearly see that there, at that 90 degrees, that there was nowhere else to go. It knew
Yeah.
there was nowhere else to go. So.
Yeah, it should have known, and I haven't written the right angle detector or the left angle detector.
No, but what he's saying is that you shouldn't need the right angle detector per se.
But I have it filtered by 45.
Okay.
That's what's
So if it's outside of 45, it throws it away.
Throwing it away, there's no acceptable
And that
path.
45 also seems like it'll be real vulnerable to the exact theta of the robot.
It's a starting point. I just made it up.
Yeah.
It's
Puta.
I guess any angle there is going to be very much controlled by, in other words, you have a very ideal robot here.
Okay,
And
sure.
It's driving very perfectly, and
Yeah.
in the real world,
No contest.
It's not going to do
It
that.
won't.
Yeah.
Yeah.
So, and maybe all that requires is to widen that a little bit.
Or maybe have it variable,
You'll
depending
find
on
that
how,
out.
what it sees and what its confidence is. It might want to change that
Yeah.
and say, let's.
Well, I think that's what he
he
was saying. I'm not sure about this. Maybe
Do you
we
even
need to
need
look
it?
at
I know that I'm gonna have to dial it in, right? I know that. But it was just interesting that it could do as well as it can with nothing more than a stupid arbitrary 45 each way, so it's really 90,
Yeah.
right? And
okay.
in a single detector.
Yeah, no, that's working remarkably well.
I mean, for as stupid simple as it is, it's actually a fair bit of code. But,
Good.
so
Great.
that's about what I've got.
Great product.
It's coming along. It's gonna be another decade or two. Look out, Tesla. Wait a minute, maybe not that.
If you could just get the roads to be like,
Is it the Sky or is that 18-wheeler? I don't know.
Well, I'll add just as a kind of a philosophical.
Call recording is off.
That good. That I have on more than a few occasions when I've actually been working on a particular design, and I'm sure other people have it similar, where my approach, which was pretty sophisticated, as I actually started, experimenting and getting feedback, I found that actually this very, very simple subset
Is all that's needed.
is all that's needed.
Yeah.
And that I have, yeah, exactly. And when you, yes, okay.
And that's the mode that I'm in, right? And so it's been this funky trade between, okay, what APIs does RoboRealm have? Okay, how am I going to partition between this code and RoboRealm? And then, damn, how do I control it? And then, oh crap, how do I make these happen in an array sequence? I mean, I've been bouncing around and back and forth.
But I think that's kind of what they would say.
Yeah.
It may actually turn out to very simple. A very simple mod to the current algorithm.
Yeah.
Suddenly you're handling all the right.
Yeah, I could just take that 45 out and let it go and see what happens.
Yeah, or maybe make it 60 or something.
60.
Yeah, that something like that is enough to not actually need a special detector.
It could be.
Because it looks like it knows that it's reached a 90-degree angle, it's just not sure what to do.
Just to know those lines, yeah.
Well,
Very cool.
A 90-degree angle, I've got a real simple robot that has no computer.
Yeah.
And it'll handle a 90-degree intersection.
Oh, yeah.
It ignores the cross line.
Okay.
Yeah,
So
because it's just not smart enough
it's
to
not
notice
smart
it.
enough.
Just fog up the lens on the camera, and everything, all the code goes away.
And that's actually funny because some of the image processing techniques involve
Fuzzing.
fuzzing
Yeah.
the image. Yeah.
Gaussian blurs.
You made a comment that I didn't really understand. The cross lines, you said the computer thinks that's one line. And I didn't understand
Sure.
that.
Wouldn't that
Yeah.
Let me show you what that means.
skeleton algorithm?
Let me show you what that means. Let me see if I can show you.
So it wasn't describing that as.
As I understand it, it's a relatively simple algorithm to determine that those are not all one
Off.
line. Yes?
Off.
Off algorithm.
They may call it something.
I haven't worried about the math. There is HOF in here. I haven't worried about the math, how it does it.
I think
Only-
RoboRealm's just
Well,
returning
only
my
knows
numbers.
that
question of how it
Hoff
does
would
it is
figure
what
out
it
those
does.
two
Is the HOF is just a sliding window?
No, Hoff
No.
is this funky transformation from.
Hoff is basically if you've got a bunch of short segments of lines and you want to try to see how many of them make up a line, straight line. Basically what Hoff does is it basically determines that this line is, if you extend it, how close it comes to the origin and what angle it is. And then it puts them in bins. And so basically what you would do if you run the Hoff algorithm on those points, you'll come up with two lines. One of them is in this direction and one is in the other direction, and you know which one you want to follow.
Yeah,
Throw it out.
populate two bins. In that case, you would have two bins, right, that basically would get full.
But,
And the bins are,
but you started with different line segments though,
Well,
right?
and you feed them in and they build up.
Anytime you do a edge detection, you're gonna come up with a bunch of short lines. You're not gonna come up with a contiguous line.
Well, the
Because-
skeleton does that.
Well, the skeleton's something else.
The edge detection. So I don't have that in this, but
Okay.
when I ran edge detection in this, it would come up with two lines. So for each edge of the black line, there was now two lines, like railroad tracks. Okay, and then
But when you got lines in a pixel environment, the lines have to be parallel to the pixels, and so it's not a smooth line, it's an offset staircase. Either they're adjacent or not, like this in a pixel environment. You don't have it really.
it's a digital thing. It's not analog, right? They're discrete things separated by,
So each one of those is a separate line if they don't, in other words, well,
It's not horizontal or vertical.
but that's, okay, but I think, so like if you look here, I think you're talking about this right here.
yeah.
So if I would go take, and
Yeah.
I think if you run your
Each one of those
If I-
lines occupies a single coordinate in Hoff space, is the way it kind of works out.
You
So
got
that ends
Hoff-
up as two
Okay.
blobs in Hoff
So-
space.
Carl, when you got there, you said I have one line.
yeah, this
And
point right
that's the
here.
confusion, is that to humans, that's not one line.
But to the computer, that's what I'm going to show you here. If we look at the variables in that point,
Look into the Hoff.
well, what we have to do is take the sample. Where do sample lines go? Sample line. We have to move this up as well. Okay, this is the issue right here. And then I'll have to reset my Git repo. At this point in the script, before I do this funky math that subtracts like that,
Okay,
okay, at this point in the script, I said to the computer, this looks like one line. And the reason I said that is that if you look at this, literally, variable right here, this segmented line array,
Yeah.
x, y, x, y, x, y, x, y, minus 1, minus 1, there's only one delimiter, so to RoboRealm, this is one line.
Oh, but if you run it through the Hoff algorithm, you can take your individual little line segments. And the Hoff algorithm, there's some trick to avoid vertical lines giving you problems, but kind of the idea is, if we're in XY space like this, and we've got a little segment like this that are kind of like such, more or less, what happens is if you look at the line equations of these, the Hoff is, they change it a little bit because you end up with some problems. But if we looked at the line equation for these segments, you remember the old, so y equals mx plus b? So really what we're talking about here is we're talking about a y-intercept and a slope. But, okay, they do something slightly different for Hoff, but it turns out that if we looked at this line and figured out its line equation, which you can do easily from, these two xy points that are known. Okay, so we take those and we end up in Hoff space, we remap to a new coordinate system. And this coordinate system, although they do something slightly different for Hoff, is the MB system. And it turns out that in this system, this line segment right here occupies some point. And this line segment occupies a very close point to that, almost the same. So that, in other words, if we had identical line segments that had the same line equation, because they're all collinear perfectly, they'd be a single point. But what happens is we have some little variations, so we end up collecting little clumps. But then with your segments that are running in this direction, it's some totally different clump. And so by, as Will was saying, put them in buckets, we can determine that, hey, the lines that belong to this clump are ba, ba, ba. And so therefore, we've got two data chunks here, and we can easily say we've got two lines. So that's well worth your time looking into that.
H-O-F-F?
H-A-U, how do you spell it? H-O-U-G-H.
A hue.
Yeah, well,
Let's-
they pronounce it Hoff, I think, H-O.
Ron, when you say those are bent, what is it you're actually bending? Is it the
The
N and B,
coefficient.
or is it the
Well,
Y?
and now when they actually,
Okay.
it's the
All right, here
perpendicular
it
distance
is.
from
Oh,
the
well, okay,
origin
Will-
to the line.
So that's just a single number?
well, hang on, Will.
And it's the angle.
Wait, don't go that far yet. No, the reason I say that is you'll confuse people. Because here's the problem with this situation is because of the fact that you have if you have a vertical line, you end up with you can't use the line equation for that. So they make a modification.
The way I defined it, the vertical line causes no problem.
Right, but I'm saying for people to understand, everybody knows the line equation. They did that. I mean, I actually can remember that. And I actually know what that means. So that's why I was explaining
I
in that
can- I
terms.
can-
But they modify it, go ahead. Yeah, okay, so they don't use this.
My,
But this is,
Well, thank you for the explanation.
No, but this is the conceptual idea. Now, there's a slight variation. He'll explain exactly.
Like in physics, they say,
My
oh,
conceptual
but that was a lie, it's really like this.
This is
Consider
your
a spherical
line
cow.
Let's say we choose a point down here as one. So what I'm interested in is if I extend this line, what I'm interested in is this distance, this right angle right here. I'm interested in this distance here and this angle here.
There you go.
Those are the two numbers I'm interested in. It's this distance and this number. Those are the two
Okay,
numbers.
so with that said, if you have lines that are collinear to that segment he just drew,
Yeah.
you end up with the same angle and the
And the
same
same
distance over and over and over.
Yeah.
Or if you're
slight
close,
variations
slight
thereof.
variations,
Yeah.
now you
It's
end
the-
up with a clump.
It's the bin.
So that's why you want a bin, and so that's why you take a summation.
Okay.
In other words, if we arbitrarily take his thing, or it doesn't matter, this thing, and we arbitrarily generate bins, we're gonna find out we get a population here in this box and a population in that box. And that's kind of the idea. But tell you what, you go look to see the people that actually wrote the
It's what this
the
window is
stuff,
right.
and then
It's
you'll
pronounced
see
Huff.
why. Hoff.
Hoff.
I think it's, I was told that's how you
So,
pronounce it.
so he found the Hoff algorithm
Oh, there we go.
in
We know this is
RoboRealm.
the real thing.
So we might have to
This-
see how it works
This is
now.
how it looks, right? So,
Yeah, there you go.
So if we go.
Oh, yeah, there's a bunch of lines, and see how they're using grayscaling to show you the
Variation.
yeah. Yeah, you end up with sine waves in this other thing.
I don't know what this extra line is that just showed up. But, yeah, so if we go to,
So they solved it for you, right?
I don't know how to interpret this, right? Because now how do I adapt that to my algorithm? Let's say we jump to this waypoint 5. Where did I go? Waypoint 5. So this is this point in space. That point on the course. So if we come down and look at the hue, what does that mean?
That doesn't help a lot.
If I turn a little bit.
A couple lines.
Well, it
I mean,
means you got
already my
a lot.
intersection says I should go this way, so screw this Hoff thing.
Ah.
Well, sounds
Wait a minute.
You know, hey, that's an interesting thought. When we got curved lines, we got. I know Hoff can detect circles real well, and they use that in detecting, I think, face detection, if I'm not mistaken.
So-
the shortcut.
Look, all these little knobs and switches, angle filter, edge influence.
That's what it is.
You might have to
Peak
study this
detection.
filter. Learn how to use it.
What are your two images? The one up there is,
Where is it on course? It's right here.
what, okay, that's in the course.
Yeah.
And what's this little square you got in the middle?
This thing?
That's
That's your Hoff,
That's the edge. That's the Hoff transform.
But that's in Hoff space,
that's
right?
the Hoff space.
So that's not real useful to you, except
Well,
it's showing that you've got.
This
You know
is,
what?
this is not really your example, because those lines, those are, the lines themselves, the angle between them is the line. In other words, those could be pointed arbitrarily, in arbitrary directions. They could be circles or spots or something. The angle from one end of of a particular segment to the other end of that particular segment has nothing to do with the line
Right,
itself.
right. Yeah, so, yeah, good, so
If you,
it's not good for doing that.
Thanks, Ron.
well, the reason I'm.
The jury will please disregard the previous outburst.
Not this part. The problem is,
Unless it's a.
Your
second
intersection.
line.
So the intersection
It's
one.
not on the
Or-
side line.
But, so here we are at the intersection.
And that tells you something, because you can look at that and say, gee, there's only two blocks.
There's only two, but now there's just one.
Carl, put
Yeah.
it on a solid
block.
line. And let's see what it shows.
So guys, we do have a time check here. We're at the top of the hour, and someone else has this room booked at 1. So we, well,
It's not here yet.
they're coming in early, an hour early to set up for their
Okay.
thing. So we got a little bit of wiggle room here. But I did want